Welcome to week 4, Organic 2 Q&A. Today we will go over the multiple choice questions and from the quiz 4. We'll also do the open response as well. We'll go over the quiz 4 because you're going to be seeing this same material tomorrow on exam 2. And then we will also go over your POGL activities, and I will do basically the POGL 21 and kind of go over your reaction mechanisms that you're going to have to see for aldehydes and ketones, because that will be a portion of your exam too. All right, so one of the first questions on your multiple choice questions was to predict the product. And you have what is called a phenol. And you have sulfuric acid and SO3, sulfur trioxide. This is called fuming sulfuric acid. And the sulfur trioxide is not charged, but that is your very strong electrophile. Now this phenol has lone pairs on the oxygen, and lone pairs are very activating. So phenol will be an ortho para director and very activating. So that means that this SO3 will add ortho and para. So I would take either ortho or para. They're going to be your major product. There's no way for you to tell really without doing the reaction or looking at information available to you to know whether it's going to be ortho or para. So as you look at your multiple choice questions, the para is the correct answer. The other ones were meta, and the other two had nitro. So that was the wrong substituent. Let's go to another question. Okay, we are choosing the reagents. So this is toluene, and we got to choose the reagents to make this compound here. And you see that what is added is this alkyl group, and it's added para to the methyl group. And you need to ask yourself, okay, is this activating or deactivating? Well, alkyl groups are electron donating groups. Even though they don't have a lone pair, they are electron donating, and they do it through induction through the sigma bond, and therefore they're going to be ortho para directors, and they are activating, which means that their reactivity is going to be faster than benzene itself. Now, you see that this is a secondary carbon. Okay, so that carbon's bonded to 2 carbons, and there's no way you can do Friedel's Kraft alkylation. Okay, that cannot happen because you get the hydride shift. So you did have a POGL exercise that kind of talked about this, and so at this point you'd want to do Friedel's Kraft acylation. And acylation means that this carbon here needs to be an acid chloride, and then you have the other ones here, and then you need aluminum trichloride. And notice I haven't even looked at the questions, the answers. So if you do this, this is going to give you this electrophile. The strong electrophile will be the acylium ion, and then this will add here, and we will add this to the para. I will just not go through the mechanism for time purposes. You have plenty of those. Okay, but that's still not the product, right? Because we have to do D um, carb, carbonylation. So we got to take away the CO group and we need to add the H2. And so we need to still go here. This is a reduction. So in order to do that, to remove this, we do zinc and mercury in a solution of hydrochloric acid. And so you can go through there and you'll see that those are your reagents. All right, the next one is predict the product. So let's predict the product here. And we have, this is Friedel's Craft alkylation. Okay, so what I would like to see you do is with the aluminum and show that carbocation, and then you get the hydride shift. Okay, so it is now this is what's going to add. This is your electrophile. So the first thing you want to do is figure out what's the electrophile that's going to add, and that's going to be the carbon that adds. Then you got to look at here and say, okay, the carbonyl group is delta positive. So if you did a resonance structure, you would see that that's positive. So that means that's an electron withdrawing group. So that is going to be a deactivator, and it's going to be a meta director. So we're going to add here. So your answer should look like this, but this is ortho, and there's meta, and there you go. So now you look, and you should see that that is one of your options, and that is the correct answer. The next one, you're choosing reagents. All right, so here we're going to add 2. So we start with benzene, and we're going to add the bromine, and we're also adding the alkyl group. Now, is bromine ortho-para director? So that's ortho-para director, and the alkyl group is ortho-para director. So since they're both ortho-para, it's not going to matter which one you add first. In order to add the bromine, you just do those reagents here. And then to add this group, we've got to do Friedel's Craft acylation because that is a secondary carbon, okay? And so we need to do the Friedel's Craft acylation, and then we have to reduce it with zinc and mercury and HCl. And if you look, there is a correct answer. The last one is predicting reagents. So we have an ester, and we are making an alcohol. Okay, so this is a reduction. Okay, so this is an ester, and this is a primary alcohol. And esters get reduced with lithium aluminum hydride. It takes NTHF. It's a very strong reducing reagent. And so there is the carbon that becomes the primary alcohol. Sodium borohydride would not work. Okay, that's too weak. So that will not work. It'll work with aldehydes and ketones. The Grignard, CH3 magnesium bromide, that would give you a tertiary alcohol. So this would have added twice. Because remember, you get your ketone, this would be your leaving group. So this would have been a tertiary alcohol. And the Jones reagent, the chromium, would not do anything to an ester. That gives us an overview of our multiple choice. Let's go to the open response. Okay, so reviewing the open response, I did say a correction. If you want to make this benzene, and then your goal was to go to this here. Okay, so if you got that announcement and made that correction, you would say, okay, how are these related? They're meta. So the first thing you would want to do is do Friedel's Craft, right? Because that's a secondary alcohol here. And so you need the aluminum trichloride and do Friedel's Craft. And what would that look like? That would give you from benzene, it would give you this. And then this is a meta director because it's a ketone. So this carbon's partially delta positive. So then we could do Friedel's Craft alkylation. All right, so that would make this compound. Right, and then we'd have to reduce with zinc and mercury HCl to give you your product. So those are the 3 steps. I said you could change that. If you wanted to try to go from here to there, how would you do it? Tricky. So I guess I would say benzylic oxidation would be good because we've got to get a meta director in there. And so that would give you this methyl here would go to a carboxylic acid. And then I would, if I was working this in the lab, I guess then you could do your, that would be a meta director. So now you could do your acylation. And what would that look like? And then you could do your zinc, mercury, HCl. I do not believe this would do anything to your carboxylic acid. So that would remove the ketone. And then you could, I would do Friedel's, I would do Fischer esterification. And, or you could have done that before here even. Okay, so that would have been fine. Fischer esterification, just methanol and some acid. And you'd make your ester. This is why this was a 1-point bonus. And nobody actually got it. That's okay. Okay, so then that makes the ester, and then esters can be reduced with lithium aluminum hydride to give you a primary alcohol. See, very lengthy. Okay, so that gives you a primary alcohol, and then to go here, you would have to do tolusyl chloride and pyridine, and then do lithium aluminum hydride again. Because remember, you can make a tosylate, and then the hydride could then make that a methyl group, and that would give you your product. So yeah, that was a little typo, and so hopefully a lot of you figured that out from the announcement and did these 3. It's still a good question though here. This is still a great question because you have to learn this is meta and you have to do that manipulation. All right, so everybody seemed to get the next 3 questions right, so that made me happy. It means you're getting out of the lectures what you need to be getting out of. So here we have a nitration reaction, so it's the nitronium that is your strong electrophile. And you recognize that this is electron donating group, so that's going to be an ortho para director And so you could give me either ortho, and you're going to put the nitro there. And I want you to be able to draw the Lewis structures. Or you could give me para. Now, keep in mind when you do your open response, I want to see as many Lewis structures, lone pairs, formal charges, electron flow arrows, intermediates as possible, because it's the only time I get to interact with you and give you feedback. If we were in a face-to-face class, I would have you at the board and turning stuff in and doing class wrappers so I could teach you. Okay, now we have a nitro. A lot of people got this. So we have our nitro, and with mercury and zinc and HCl, you recognize that the nitro got reduced to an NH2. So this is that reagent again that can take the carbonyl off of a ketone, and it also can reduce a nitro to an amine. And then the next one, we have a primary alcohol. It's actually a primary benzylic alcohol. And with chromium, the Jones reagent, it will go all the way to the carboxylic acid, so oxidation. So very good. Okay, let's look at question number 2. The desired product. This was a very challenging one, and I was impressed with a lot of people that got it correct. So some people wanted to do fluoride and then maybe something like this. And that reagent doesn't work. Okay. If you want to put a fluoride, there's only one way to do it. And you were supposed to go from benzene. So if you take benzene and this, and you would see when you have two substituents, you say, how are they related? And these are para. So is fluorine a para director? Yeah. So you can add that first. Okay, so then you take benzene. In order to get fluorine, you got to go through this process. You got to go through nitration. Okay, so then that puts a nitro group. And then you got to reduce that. And that reduces the nitro to the amine. And then you got to go through this diazotization. So it's just, or you could just write HNO2. This is nitrite. Okay, so it's nitrite, and it actually makes the diazonium. Okay, so this is a diazonium, and it's actually an arene diazonium. And this can actually do a displacement. So now you can use this reagent here, which basically is the F, and now you can, this can leave. So it leaves 78% of your atmosphere is nitrogen. Okay, so this is the world's best leaving group. Okay, you got to have the world's best leaving group in order to get fluoride to do a nucleophilic displacement on a sp2 carbon. This is a very hard thing to do. Okay, and so now we have the fluorine installed. Okay, so how are we going to go with this? Some people wanted to give me something like this. Okay, this reagent's not going to exist. Is that a functional group you've learned? No, but you do know that this is an acid chloride, and you have 1, 2 carbons, 1, 2 carbons, and you know you can just do Friedelscraft acylation. So here's the electrophile. I always like to figure out what my electrophile is, and then we have a para director. So this is going to give you this compound here, and then that's a ketone, and you know that sodium borohydride will reduce the ketone to a secondary alcohol. So that would be how you would make that desired product. I like that people are starting to think of these long sequences and synthesis. Let's go to 3. We have, this is called anisole. Okay, it has lone pairs on the oxygen. This is definitely electron donating group, and this is an activator. I want to say this is about 10,000 times faster reacting than benzene. And so that means it's going to be an ortho-para director, and your reagents that you're adding is a Friedels-Crafts acylation, and I wanted to see the mechanism. No shortcuts on this, folks, and you're going to see this on your open response again, too. Okay, so what I'm happy with is you could just show your acylium ion here. You got to keep in mind, I write my exams as if you have no access to any notes whatsoever. Okay, so in class, I expect you to be able to write your strong electrophile. You don't have to do the whole aluminum coordination and all that. But I notice people are giving me that because they're looking it out of a book or they're looking it up. But what I expect is what you would do here is make your electrophile. So this is your strong electrophile. And then you can just pick a position. So ortho or para, let's go with para. And then I expect your electron flow arrows to go there. And I guess you don't really have to go up there because you're not going to have a issue with octet rule. All right, so then I want to see the sigma complex. And I know some people are doing this a little different, and it's not incorrect, but it's not how I teach you with your resonance structures. So if you're going to do it where you put in 3 resonance arrows in order to attack and make the sigma complex, then you had better also gotten all your resonance structures. Okay, so some people are putting in a lot of electron flow arrows. But the problem with that is you do lose some of your resonance structures. So this is your sigma complex. So I'm looking for that. Now I want to see some resonance structures. So in resonance structures, I don't want to see too many electron flow arrows. In this case, when you've got a carbocation, you just have one. And you draw in all your sigma bonds. You have your hydrogen there. Now you have your positive here. You have your oxygen. You should have 4 resonance structures for this. Okay, now we have these electrons go here. And now the oxygen gets the positive charge. I expect to see formal charges. Now I want to say something here. This is the most important resonance structure. This is why it's 10,000 times more reactive than benzene. All right, so now we have this here, and these go there, and we're going to put the positive charge on this carbon. We draw everything else the same. And then you got to show your sigma complex. I like to see something like this here, coming and taking the hydrogen, going towards there to see what we call re-aromatization. And you can write that on there, re-aromatization. The more information you give, the more I understand that you understand. The whole point of your assessments is for you to demonstrate to me understanding, so I, as your instructor on record, instructor for the record, says confidently that you have mastered this understanding. Okay? When you do not put all your details in there, I cannot fully give you a grade to say, yes, you have mastered this concept. And that's why I look for the resonance arrows, such as these resonance arrows, the double-headed arrows, the certain resonance structures that make the compound more activating. All right, so now let's look at the last question on this quiz. Question number 4. We had a nitro compound, and this was Friedel's Craft alkylation. And I wanted to see the mechanism. I wanted to see the nitro group. That was worth a half a point. The Lewis structure. Read your problems thoroughly. So I wanted to see this. And I wanted you to know that that was deactivating. And by drawing the structure here, you see that it puts a positive charge on this nitrogen. Okay, even though this is neutral, you see this is neutral, the nitro has a plus minus, but the nitrogen has a positive, so this makes it electron withdrawing group, which is deactivating, which is a meta director. And that's what I wanted you to see in this quiz. So now when you have this, all you have to do is write CH3 plus. Okay, that's your strong electrophile. And then you got ortho meta here, so it's the meta that's going to add here. And then you draw your nitro. And then we're going to put the CH3 there. Just draw in our hydrogens. And then we got to put a plus here because that's our sigma complex. And then I expect you to be able to draw 3 resonance structures. So there's 1. There's 2. And then this is 3. Now, if you were to draw a resonance structure where you put the methyl group on the ortho or para position, you would see that you would generate a positive on the carbon that's bonded to the nitrogen right there. And that positive positive is so electronically, energetically unfavored that is why you don't get orthopara. You would get 0. All right, and then we'll draw the product. Excuse me. This is called re-aromatization here. So when I actually go from the sigma complex to this, then that's re-aromatization. And that is what I expected to see for full credit. Let's look at your POGL exercises, POGL 21, because I think I've given everybody pretty much feedback on the other ones. And then we just need to look at our aldehydes and ketones and understand what the expectation is for tomorrow. So everybody seems to be doing 11 okay. And I don't want to work all of your problems, but I'm going to do, I'll work the mechanism for 12A. I expect you to be able to do that. And then I think that is, and I'll do the Vidig. So 12A, and I will work 13C. Okay, so those are the 2 I'll do from your POGL. So I do still have quite a bit of POGL out. All right, so 12A, I want to see this mechanism. So make sure if you're going to turn in your POGL that you show the mechanism on all of these so I can give you feedback. And if you get your Puggle turned in by 7 today, I'm going to try to give you feedback before tomorrow. So if you do your Puggle, you'll see that this is a ketone and a diol. This is actually ethylene glycol, which is antifreeze. Very bad for you. The first step, step number 1, there's about 6 steps to this mechanism that you're going to have to do. And step number 1 is protonation of the carbonyl oxygen. And because ketones are weak electrophiles. And so this activates it. So the first step you have is protonating that oxygen. Now you can have the nucleophile come in. And so alcohol is the nucleophile. So step 2, nucleophile adds. And then you draw that product. And there's no shortcuts on this. You're not going to get full credit. Okay, so the goal here is step 3. You want to deprotonate to make the hemiacetal. So this is a new, and so you're also regenerating your acid. So the water then will deprotonate here. And when you make your hemiacetal, it needs to be neutral. Okay, we don't need any positive charges here. So this is your hemiacetal. It has this is your hemiacetal. It has an OH, that's the hemi, and that carbon also has an OR, which is the alcohol, acetal. Now, we're going to make water a good leaving group. So this OH needs to be protonated again, because the goal now, first step, the rest of this is water to leave. So OH will not leave, so if you draw it leaving, then it's wrong. So we need to protonate it. All right, and we're not taking any shortcuts here. So we will do every step. It's one of the requirements in organic chemistry. Now, you have to, step 5, we are going to reform carbonyl, and the water leaves. So this goes here, and then it leaves. Okay, so here we have the carbonyl, and now we have the step 5, step 6. The nucleophile adds to this activated carbonyl. All right, so we have this oxygen here, and we have this oxygen here, and now we have to deprotonate to make the acetal. And then we're also regenerating our catalyst, which is the H3O+. Now, a lot of times I use tosic acid. Whenever you have tosic acid, because that's a nice organic acid, you can just go with H3O+. Okay, so there's your mechanism, and this is a protected acetal. Now I want to talk about the acetals a little bit. So if you have a compound here, and they're great protecting groups. Okay, so what you can do is you can add 1 equivalence, para-toluene sulfonic acid, and you can protect the aldehyde. Okay, so aldehydes react about 10,000 times faster than the ketone. So what you would do is you would protect the aldehyde as an acetal. Okay, and then you could do sodium borohydride. And you see how you could reduce that to an OH. And then you can add acid and water. Let me help you here. That just doesn't look right here. Okay, then you add acid and water and you can release it. Okay, and that's how you could synthesize a compound such as that, where you have a very reactive aldehyde, you protect it as the acetal, and you can do chemistry on the ketone, and then you release it with acid and water to release your protected hidden aldehyde. Okay, so that's very common that you'll see. Let's also do the Wittig, and let's do actually 13C. So the Wittig, so 13C, it asks how to make these compounds. And so Wittig reaction makes an alkene. So you would want to take that alkene here and 1, 2, 3, 4. So here's a ketone, and then you're adding this carbon and that carbon. So that would be CH3. This carbon's bonded to phosphorus. The phenyl groups here, and then this, you could do a double bond like this, or if you wanted to, you could do this, which is CH2 phosphorus, pH3, but you'd also need base to generate this, like sodium hydroxide or something, to generate the ylide. Okay, or you could just, I'm happy with you just putting a double bond there. And then what's this mechanism? The mechanism here is the oxygen will bond with the phosphorus, and this phosphorus carbon will bond with that carbon. And then you can go ahead and write CH3 and the hydrogen here, and then the phenyl. And this is called the oxaphosphatane. It's a four-membered ring, and then it does a 2 + 2 electrophilic recyclization. I tell you that phosphorus loves oxygen, so phosphorus is going to hold on to that oxygen and it's going to make a double bond with the oxygen. This is triphenyl phosphorus oxide, and then you release your double bond there with, and you would get a mixture of cis and trans. That one right there is cis, and then your trans would be right there, right? Because this between the hydrogen and the methyl. The methyl's the higher molecular weight between the methyl and the ethyl. The ethyl, they're on opposite sides, so this would be your trans and this would be your cis, and you would get two of those. Okay, so make sure you are going through all the lecture materials and working your problems, and you should do all right tomorrow.